Hello everybody, my name is Mark Prandolini and I work at the University of Hamburg. I am also co-founder of the firm Class 5 Photonics. This work was in collaboration with DAISY, a Helmholtz Institute. So the project I want to present today is high power 9 micrometer laser source for spectroscopy and HHG. Some of the topics that I want to cover today will be the design features and some of the terminology that we'll be needing later in the talk, which then leads us to a material study that we conducted on important non-linear materials for the production of mid-IR sources. And finally, I want to present our first results. I hope you enjoy this talk. Why might you need a mid-infrared laser source? It turns out that many important biomolecules have their vibrational resonance within this region, which is called the fingerprint region. And in addition to small molecules, there are also many applications in solid-state physics. I've given one example of a Dirac plasmons in graphene, which has a resonance at 9 micrometers. Other systems with mid-infrared resonances include polarons, Landau level transitions, magnons and phonons. The next question I want to address is why might you need high power? By high power I mean sufficient pulse energy times repetition rate, and I've provided here 3 examples. The most obvious example is imaging, where each point requires sufficient pulse energy to create enough signal to noise, and then you've got to scan across the whole image, which requires a high repetition rate. Other examples include 2D mid-IR spectroscopy and high average power HHG attosecond sources. I would now like to talk about the main technology we use at Class 5 Photonics, which is OPCPA, Optical Parametric Chirped Pulse Amplification, which is closely related to difference frequency generation, DFG. This technology offers broadband amplification, minimal heat dissipation, especially compared to conventional lasers. They're tunable and offer high gain in a single pass, which means our lasers can be compact as well as preserving the CEP. Now, in a conventional laser, electrons are pumped to the excited state. They decay, giving off heat to the laser transition. In an optical parametric amplifier, no energy is stored in the crystal. The energy is transported from the pump to the signal and idler via a second-order process. And in particular, the DFG equation, the idler frequency is the pump frequency minus the signal. I now want to outline the general design features of our compact mid-IR laser. We begin with the pump laser. We take a commercial ytterbium laser, which is a well-established technology, with a fixed wavelength of 1 micrometer, pulse durations between 0.25 and 1 picosecond, and powers between 100 and well over 1,000 watts. They come in 3 varieties, InnoSlab, thin disk and fiber, and Class 5 can help you with the decision which one to use for your particular application. Well, the heart of the system is a single DFG stage, pumped directly by the pump laser, and the seed is supplied by a white light generator plus OPCPA white dwarf from Class 5 Photonics. It has an output wavelength between 1.14 to 1.36 micrometers. These 2 signals combine, and the final output idler, which is the mid-IR, has a wavelength range between 4 and 11 micrometers. Now, as you can see in this system, there are 3 beam splitters. The first two are just standard beam splitters, but the third one is a very special one, splitting the very high energy of the 1 mu pump together with the signal and separating out those waves from the mid-IR. And in all future slides, when I talk about efficiency, I talk about the starting 1 mu pump energy and comparing that to the final mid-IR energy after all the beam splitters. As discussed in the previous slide, the critical stage is a single DFG crystal combining the pump and signal waves and producing a mid-IR idler wave. Now, in most cases, it turns out that the pump wave generates most of the heat within the crystal. So Class 5 Photonics, together with our partners at DAISY, decided to do a material design study of high-power lithium-based crystals. The results of this study are published in Optical Materials Express. On the right-hand side of this slide, you see our experimental setup. We had available a 200-watt ytterbium YAG inner slab laser. Our crystal aperture size was 9 × 9, and where possible, all 200 watts was pushed through the crystal. The temperature profile across the crystal was measured with a thermal camera. The beam profile, which could measure damages, as well as measure the nonlinear refractive index, was measured with a Basler camera. The next 3 slides, I will summarize our results. Using the thermal camera, it was possible to determine the total heat absorbed in the various crystals. The example shown here is of LGS. So for the first case, A, we set the laser at 1 megahertz, therefore reducing the pulse energy for each pulse, and ramped the laser from 0 to 200 watts. The response of this particular crystal was linear, and therefore we could determine the linear absorption. In the case of B, we reduced the rep rate, therefore each pulse energy was 5 times greater, with a maximum pulse energy of 1 millijoule at maximum 200 watts. In this case, we could see non-linear absorption within the crystal. From these graphs, we can determine the linear and non-linear absorption for LGS, and this was repeated for all crystals. In another set of experiments, the Basler camera was used to monitor the beam profile after the laser had passed through the nonlinear crystals. Again, we did the experiments at 1 megahertz and 200 kilohertz, ramping through 0 to 200 watts. Again, I show the example of LGS. At 1 megahertz and relatively lower pulse energy, you can see almost no Kerr lensing. However, at the lower rep rate of 200 kilohertz, you can see a decisive degree of Kerr lensing. And from these results, we can determine the nonlinear refractive index. I present a summary of our published results from these experiments. I should say at this point we used a thermal imaging method which was developed within our group. The thermal imaging method provides upper limits to these parameters under realistic high power operating conditions, and a comparison to other methods is discussed within the paper. Okay, as you can see, the best crystal for high power applications is LGS. It has the largest band gap, relatively good nonlinear optical coefficient, with a very high thermal conductivity, very low linear absorption, also low 2-photon absorption, and nonlinear refractive index. with a very large damage threshold. Other crystals that could be considered would be LIS, LIS, which would be very good for a narrow-band tunable system. Class 5 can advise you on which crystal to use for your particular application. I will now demonstrate the potential of our high-power mid-IR laser design. We had available a 200-watt ytterbium YAG InnoSlab laser with an output at 1 micrometer. We scaled the laser down to 40 watts at 200 kilohertz, and using LGS as the DFG crystal, we achieved the following tuning curve, which was tunable from 4.2 to 11 micrometers, with a broadband signal between 8 and 9 micrometers. Again, using 40 watts at 200 kilohertz, we achieved pulse energies, mid-IR pulse energies over 1 microjoule across most of this range, with a peak efficiency of 1.1% between 8 and 9 micrometers. The dip in the curve that you see between 6 and 7 micrometers is due to water vapor, which can be eliminated by purging the system with nitrogen or another inert gas. From the previous tuning curves, I have picked out the best efficiency and the broadest bandwidth, which was around 9 micrometers. To summarize this particular curve, it was pumped with 40 watts at 1 micrometer. It produced 440 milliwatts at 9 micrometers. Pulse energy was 2.2 microjoules at 200 kilohertz, with an efficiency, a total efficiency, of 1.1%, which is directly from the pump to the mid-IR output. And finally, the bandwidth is broad enough to support a Fourier limited pulse of 50 femtoseconds. What are the power limits of our system at 9 micrometers? Well, as I mentioned before, all previous experiments were conducted at the lower pump power of 40 watts. There were many reasons for this decision. Firstly, there was safety. Secondly, we wanted to test all the optics before the full thermal load was applied. This is especially important for that last beam splitter, separating out the pump and the mid-IR signals. However, we did a material study of all important lithium-based non-linear crystals at full power that we had available, which was a 200-watt InnoSlab ytterbium YAG laser. This study demonstrated the properties of all crystals at such power levels, and from the derived material properties, we can predict the following. So if we were to pump, instead of using 40 watts, the full 200 watts, we expect 2.2 watts at 9 micrometers, with pulse energies of 2.2 microjoules at 1 megahertz, and we expect pulse durations to remain under 100 femtoseconds. I hope you enjoyed this talk and got some insight into what we are doing at Class 5 Photonics concerning our mid-IR project. Of course, the system I presented was only one option, and we are open to discuss your particular mid-IR application needs. So if you want to know more, please get in touch with us, or you could contact me directly. I thank you for your attention.